Hi, and welcome to the Microsoft Virtual Academy and the presentation on software development fundamentals. My name is Jerry O'Brien, a technical content development manager here at Microsoft, and I'm joined by, believe it or not, my manager, Paul Party.
Hi, I'm Paul. I'm a content development lead here at Microsoft.
And what we're going to present to you in this session is module number 2 from the software development fundamentals, and we're going to focus on core programming in this module here. Core programming revolves around the foundational concepts that you'll need to know for any programming language that you're working on. Although the samples we'll be demonstrating in here will be in the language C#, they really pertain to just about any programming language that you're going to program in the industry. So in this module, we'll take a look at how computers store and manipulate information. We'll give you a brief introduction to some data structures, which are ways of storing multiple pieces of information inside the computer. We'll introduce you to what an algorithm is and kind of give you a couple of examples for what those are, kind of get your mind thinking about how you'll get into the programming aspect of solving problems. And then we'll present some of the core functional aspects of programming, which deal with decision structures, how we make decisions in the computer program, and how we control the flow of our program code. Then we'll talk about repetition, which is one of the things that computers are really great at doing, is reiterating and doing something over and over and over again many times without complaining about it. And then we'll talk about one of the things that all developers say they don't need, which is how to handle errors in their program. So we know as software developers, errors do creep in, so we'll talk about what those are and how we can handle those in our programming. So the first aspect we want to take a look at here is computer storage and processing, and this focuses on how a computer stores information and how it processes information so that you can gain a better understanding of why you have to deal with the syntax of programming languages, why you have to restrict your data information that you're putting into the computer into certain types. So it kind of explains why we use data types, why there are restrictions and limits on what those can be. So we'll focus on what those specific aspects are and kind of what drives the computers in the background. Now, this is not information that you necessarily really need to know to be successful in programming, but it is great background information, and it helps you become a more effective and a more efficient programmer. So computer storage and processing, we take a look at it from the perspective of how the computer deals with the information and the data that we'll put into it internally. And it's important to know that computers deal with binary information. So the numbering system that we have on our computer systems focuses on a binary concept. And if you're not familiar with what binary is, it's basically two discrete phases. We can consider it to be off and on. We might say there's a yes or there's a no, but that gets into different aspects we'll talk about later. But from the computer's perspective, internally in the circuits, we're either dealing with the presence of a voltage or no voltage. So this is where your binary concepts come from. And we represent those in the computer through a binary numbering system which focuses on two discrete values, a 0 or a 1. The ability to represent real-world data that we use, such as the numbers we focus on a day-to-day basis, or the characters, the letters that we have in our alphabets, or in foreign languages such as simplified Chinese, or in the Japanese languages, even in other European languages we might run across. We have to have a way of representing those character sets, and that's what they're referred to. These are the characters or the symbols that make up the words and the letters that we use. And in order to represent those internally in the computer, a 0 or a 1 isn't sufficient, so we have to represent them with multiples of these zeros and ones. And they're represented in things called bits and bytes. So a 0 or a 1 is known as a bit in a computer. And if we combine multiple bits together, we start to create other representations such as bytes and megabytes and terabytes, etc. So they grow larger and larger depending on the amount of bits that we've included in it. On this particular slide, you'll see on the left-hand side, we're showing a representation of binary numbers. So those are the zeros and the ones. The bottom figure represents the CPU, so the central processing unit for the computer. And then the top one represents the memory that you might have in the computer. We don't have representation for long-term storage, which are your hard disk drives and your optical drives, such as DVD-ROMs and things like that. But it's important to note that when a computer executes a program, it cannot execute the code directly from a storage device such as a hard drive. It has to access that information directly in computer memory. Now, computer memory is expensive, relatively, when you take a look at the price of storage such as hard drives and DVD drives. And so therefore your computer is not going to have infinite amounts of memory. We only have a certain amount of memory that we can actually use in the computer and to store that information. So that kind of talks a little bit about the restrictions that we'll focus on the data types a little bit later on in this presentation. But it's important for you to understand we can only load a finite amount of information into the computer memory at any one point in time. So we talked about the representation of the characters, strings, the values that we use on a day-to-day basis for words and sentences. And on the right-hand side of our screen, we can see something that's known as an ASCII chart. And this goes back to the days of long before Windows, long before the computers that you're using today. And the ASCII chart was a way of representing values such as special symbols, punctuation marks, letters, and numbers in our binary system. And you'll see representations in here. You'll see under the column on the left-hand side, you'll see decimal representations. You'll see hexadecimal representations, which are another numbering system that we use in computers. And then you'll see either the characters or the codes in the remaining two columns. And you can see that that's how the numbers are actually represented within the computer itself. And you'll see this is indicative of what we might choose or see in a normal North American language infrastructure, so the English language. We've got punctuation marks, we've got numbers, and we have upper and lowercase letters and some special characters. And those are represented with the specific codes in the computer. So this is basically how a computer stores the representation of these letters and numbers by using decimal values or using hexadecimal values inside the computer itself.
So Jerry, programmers aren't going to need to program in ones and zeros, right? They're not typing in ones and zeros as they're programming. So how does a modern programming language relate to that decimal system? What does the programming language do?
Yeah, so that's a very important point, Paul. And you say that programmers don't have to write in zeros and ones. They did at one time. So fortunately today we don't have to deal with that. In the early days of computers, they used punch card systems where the binary values were represented on these little paper cards. They had little holes punched out in them, and they had stacks and stacks of these cards that they would take and feed into the computer. And if they were out of order, the program didn't work correctly. So fortunately now we have something known as programming languages, which are a little higher level. And the programming language allows you to write your code in an English-style syntax, if you will, and then we can represent data, we can represent instructions through these binary concepts in the computer. And the programming language actually, again, we're writing it in an English-style language, and there's a compiler in the background that takes those English version instructions or the high-level instructions that we write and the data that we include in our program, and it actually exports it into a binary version that the computer is able to understand. So you don't need to worry about how the compiler takes care of that. We've got developers that write the compilers and developers that are responsible for translating our instructions and code into something that the computer understands. But the other aspect too, and to kind of answer another aspect of Paul's question, was once we do the compiling, there are specific computer platforms. So if you're looking at the older versions of Apple computers used to run on a PowerPC chip. Windows-based PCs were running on Intel CPUs. The tablets and the smartphones that you're using today operate on Atom CPUs or some other type of a CPU. Those central processing units have specific instruction sets. And so what that means is that inside the CPU and the functionality of it, it understands what an instruction is versus what the data is that we want to process or act on. And so this is how the computer knows whether it's given an instruction that it has to execute or whether it's looking at data that it has to pull out of the memory and do some functionality on it. So it all boils down to instruction sets and compilers and the different CPU architectures that we're working with. Again, as you program in things like C# and Visual Basic or C++, Java, whatever your chosen language is, you don't need to worry about that. You'll focus on the key words that are a part of the language, the syntax for the language, and the data types that you use in it, and you use those as the building blocks for your program as you go through writing your code. The compiler handles translating all of that information into the machine instruction code. So that's actually a good segue to talk about our next slide, which focuses on things such as variables, constants, and data types. And these are aspects that you'll need to understand in order to write code successfully in the programming language of your choice. So before we talk about the data types, let's talk about what we use to store this information in the computer. Again, remember that we said the CPUs have specific instructions, and those you can consider to be the keywords in the programming language that you're using. You cannot use these keywords as name storage locations for information. They are the instructions that the computer will execute. So it's important to understand that when we talk about something called a variable. Now, computers deal with memory addresses that are typically in either a binary or a hexadecimal address, and if you work with a programming language that allows you to export or look at a memory address, you'll find that those memory addresses are in a hexadecimal format. And if you don't understand hex, sometimes it can be difficult to read, but not only that, when you have large amounts of memory, the hexadecimal strings can get rather large. You don't want to have to remember those when you're coding. So what we do is we create named storage locations that we refer to in our code that will then be directly mapped to these memory locations. And the compiler and the computer take care of that. You don't have to worry about that mapping. All you need to worry about is I created a named storage location. That's how I'll access that data to either write to it or read it in my program itself. So a variable is something that we use as a named memory location that by its very nature and because of the name variable has the ability for us to change the values that are assigned to it. So we will create a variable name, and we'll see examples of that in some of the demos that we do a little bit later. And the variable name will point to a memory location in the computer, and it will store the data that we say we want to put in it. The key piece about a variable is that we have the ability to store information in that variable. We can read the information back from the variable, and during program execution, we can actually change the content in that variable. So again, this is why we call it a variable, because it's ever changing.
So to think about a variable as just a container of some sort, just a holder. So most people have filled out an online form at some point. So if you have a form that has first name and last name, you'll have the first name field, I'll put in Paul, last name field, I'll put in Party. Behind those fields that you're filling out in that form, there's probably a variable that's holding that data. So there would be a variable for Paul, there would be a variable for Party, maybe called first name and last name behind the scenes.
Yep.
So the variable is just a holder for that data that you're entering.
Exactly. And that's really a great example too, Paul, because if you think about filling out a form, whether it be, typically an online form, we'll say on a website, the information that you put in, we can have multiple users filling out that form. So even though we've got a variable called first name, anybody can be putting their first name into it. So yeah, it's a great way of looking at it. The other name memory location that we have to work with in our code is known as a constant. And the constant is something that is similar but yet different to the variable. So we know that we can assign values to a variable, and we can retrieve them, and we can change them. With a constant, we can still assign a value, but we have to do it at the time we create the constant itself. We can read the value from that, but during program execution, we're not able to change the value in there. That's actually an illegal instruction in terms of what the computer programming language expects, and it will tell you if you attempt to do that in your code itself. But when we talk about constants, we actually have two different types. There are what we call constant values that we would assign in a program, and then there are literal constants. And an example of a literal constant would be the number 1 or the letter C. Those are literal constants because we can't change that value. The number 1 will always be the number 1. The letter C will always be the letter C. So those are known as literal constants, and you'll see those when you start writing your code. Now you can assign a literal constant to a variable. So if I create a variable to store a number, and I call it number, I can store the value 1 in that number. But the value 1 will never change, but the value I've stored in number could change. So again, it's a little bit different when you look at it from the perspective of what you can and can't do with it. Constants are really important in programs because we use them to represent a lot of the time literal constant values. So as an example, if you're writing code in a program and your program is going to calculate the area of a circle, well, what's a familiar mathematical constant that we have in there is pi. And instead of you writing in your program each and every time 3.14, 159, and this big long pi value, however numbers of precision you want to put in there, you can represent that value in your program by creating a constant called pi and assigning that 3.1419 value to it. So it serves two purposes. One is it creates a named value, which makes it easier for you in your code later on because you can use pi instead of putting that number in every time. But it's also a way of kind of self-documenting your code so that when you see that in a formula later on in your program and you see the word pi, you know what it is and you know what it's being used for. Whereas you might look at 3.14 in your program code later and realize, well, is that just a value that I put in here, or does it actually represent something? So constants are a great way of representing those values for us. Now let's take a look at our slide again, because the last part of this one focuses on data types. And remember how we talked about representing the values in our program that we use in the real world. This comes in the form of numbers and characters in something known as a special type. And we'll talk about the special type last, but we know that we will need to store numeric values in our program. Could be for mathematical calculation within the program. They could be used to represent telephone numbers, zip codes, different things like that, right? So we need to store numeric values. We also need to store character values, and those can be single characters or they can be words and phrases, and we need a way to represent those in the program. So each programming language represents those values through something known as data types. Some call them intrinsic, some call them implicit, some call them fundamental, but they're a part of every programming language. And it's not to say that the values that you're seeing on this slide, the specific names in this left-hand column of data type, will be exactly the same in the programming language that you choose to program in. These are representative of what C# makes available. So the first one is a byte, and really this just allows us to store a single byte, or 8 bits of characters. And it's a relatively small type, and we can store values from 0 to 255. That's what we're representing. So it stores a numeric value, but also called a byte. And we can use it in a bunch of different ways. And as you start getting into programming a little bit later on in your career, you can actually start to focus on what you can use a byte for, because we can use it for more than just numeric characters or numeric values, sorry. We can use it to store all kinds of other information that is representative of something else. We don't want to go into it here because it can get very complex in what you can use byte to represent, but just know that we have a range of 0 to 255, and it will store 8 bits of information, or a single byte. The other numeric types, we'll come back to char here in a minute, but we've got a short, an int, a long, a float, and a double. These are all numeric types as well, and those give us the ability to store numbers in our program, but we choose which one we use based on the value that we want to store in that particular variable. Now, at one point in time when we were writing programs back in the early days, and for me, early days are early 1980s, where I was focusing on writing programs for the Commodore VIC-20. Some of you may or may not know what that is. Of course, Bing is your friend. Go ahead and look it up and see what it looked like. It had a whopping 2 kilobytes of memory available for you to store information in. That meant that as you were writing your programs, as you wrote your code, you were very cognizant of how much room your data was storing, or how much storage your data required in the program. So when we take a look at these values on this slide, we see that the smaller valued numbers, such as the short and the int, were probably the ones that we would focus on mostly, because they stored smaller values, which meant they took up less memory in the computer. Today, you can still focus on choosing the smallest data value possible for your data that you want to store in your program itself. But there's a bit of a shift in the programming industry now, where we're starting to focus more on developer performance or productivity as opposed to computer performance or productivity. So in other words, if I have to spend my time as a software developer worrying and wondering about whether I should store my value in a short or a double, some people look at that and go, well, that's a waste of time. Just store it in a double. Who cares? Move on. Computer's got lots of storage information. It's got a lot of processing power. We don't need to worry about that anymore. So the programmer efficiency becomes more important than computing efficiency.
So this raises an interesting question, Jerry. Why not just have a big bucket? Why have all these different data types? Why not just have a bucket called storage, and you can put any type of value into that variable? And in fact, a lot of programming languages have JavaScript, for example, has var, which is essentially a generic storage location, and you can just put anything in there, numbers, text, whatever. So what's the purpose of having all these different data types to store data in?
Yeah, so again, great question, Paul. And one of the biggest reasons being is that a computer needs to know specifically what the data is that you're assigning it because of the operations you might perform on it. And to give you an example, we can, in programming, use the plus sign, which for most folks we know in mathematical terms allows us to add numbers. So let's say as an example that we just chose a generic storage variable, as Paul mentioned, and I have a number value stored in one of those variables, and I have a textual value stored in another one of those variables. I haven't told the computer what those are. As far as the computer knows from this concept is it's just data, so it doesn't matter what it is. But what happens if I want to add that information? If I put that plus symbol between my first variable and my second variable, the computer is going to look at it and go, what do you want me to do with this? I can't add a text or a character to a number. Mathematically, it doesn't make sense. So what am I supposed to do with it? And this is a very important aspect to that we should talk about from the perspective of how a computer functions as well. And that a lot of people go through the process of blaming, oh, I can't get into my banking system. Oh, the stupid computer is down, so the stupid computer doesn't know what it's doing, and they're always blaming the computer. But it's very important to remember that realistically, a computer is not smart. A computer is not able to perform things on its own. The computer has to be told explicitly what to do. So therefore, if we don't tell it what the data is that we're storing and what type of data that we're storing, it doesn't know how to interact with it or how to act on it based on the operations we might be trying to perform. But another key aspect too is when we're storing the information, when we tell the compiler that we want to store values in a variable, by giving it a type, by giving it a specific data type, we are also telling the computer how much memory to set aside. So it knows how much storage we're going to need for this specific program. Remember, going back to the concepts of how a computer stores and processes information, it cannot access memory or access program instructions and data directly from a storage device such as a hard drive. It has to load it into memory. This is where the computer knows to tell, or let's say your application has to tell the operating system how much memory it needs in order to load this application in memory. And if we're loading multiple applications in memory, we might not have enough, or the computer might have to deal with swapping things out to the hard drive and doing this whole memory swap of information to load one active program in and unload an inactive program. So it's very important that the computer knows how much memory it needs to allocate to these data types and what the specific data types are for the interactions it might be doing with it.
So by using data types, you end up improving the performance of your application, and it also reduces errors. So the computer will know how to treat those data types without having to make a decision, and sometimes those decisions could be wrong. So by using data types, you avoid some of those problems.
Yeah, exactly, and that's a good way of explaining it as well, right? So let's switch back to the slide again here for a second, and we'll cover the remaining ones that we focus on. So that we talked about numeric values there. We can also store characters, individual. So if you look at the char value in the left column, which is the second one down, second row down, it will store any Unicode character, and it's important to note Unicode because this represents multiple characters from around the world. And when we talk about storing information in a computer, we have to represent as many characters as possible so that we can deal with local languages in our applications as well. But a char is a single character. We can represent it as the letter A. We can represent it as a comma or as an exclamation mark. That's a char value. That's a single value. But what if we want to represent words or phrases or sentences? Well, let's come a little further down that table. The second from the last item is known as a string. And a string really it's a string of characters. So it's a string of individual characters. Consider it an array, if you will, of characters that make up those words, phrases, and sentences. And finally, the last one is a Boolean, which is known as a special data type. Not all programming languages represent it the same. Some will represent it as a true or false. Some will represent it as a 0 or a non-zero value. Some are very explicit in saying that, no, we represent it as a 1 and a 0. So again, you'll, as you get into your different programming languages, take a look at the documentation to ensure that they do support the bool in the first place and how they support that. And again, Boolean is just simply, it's a true-false. That's all it works out to. So again, very high level, these are variables, constants, data types that you'll work with in your program itself. And these are the core pieces that allow you to represent the real-world data that you'll need to work with in your program. So now that we've seen how we can represent single individual pieces of information, a character, a number, words and sentences, what have you, we now need to talk about how we can store multiple pieces of potentially related information in our system. And this is where we focus on data structures. Now, before we delve too deeply into these, it's important to note that, again, this MVA is designed to kind of help you prepare a little bit for that Microsoft Technology Associate exam on software development fundamentals. We can't cover everything that you'll need to know. What we're going to focus on in the data structures are some of the ones that you will encounter on that exam. The data structures that we'll cover here are not complete. Different programming languages implement different types of data structures, but we're going to cover kind of the core common ones that you'll encounter on the MTA exam, and that's why we've chosen these ones specifically. But note that there are more data structures available, and you can still get a general understanding of how they work by looking at how these specific data structures function as well. So let's look at our first one. We'll take a look at, in this module, arrays, stacks, queues, and dictionaries. So 4 different ones that we'll focus on, kind of let you know what they look like, how they're implemented, where you might use them, and then we'll see some actual code samples of what those look like. So the array is the first one that we're going to take a look at, and you can consider an array to be simply a collection of similar data types, which means a collection of data types that we're putting in. Could be any particular type, but one of the aspects about arrays that we need to be aware of is they're designed to store the same data type. So in our array, we really are going to typically be storing string values or a collection of number values, or as you get into object-oriented programming, you could store a collection of objects, but they typically are the same type. And arrays are accessed through indexes. Now, an array is what we might consider to be the ability to, best way of describing it, I guess, is it's a random access data structure. So we can access the values in this array at any time, in any value, in any order, simply by using the index value. So as we look on the slide, we see that in the left-hand column we have the index values, and in the right-hand column we actually have some string values representing what we might store in this array. And for simplicity, they're just called item 1, item 2, item 3, what have you. And on the left-hand side is the index that we would use to gain access to those values. Now, the important thing to note is that most programming languages today are 0-based when it comes to arrays. So in other words, they start their counting at 0, not at 1. So that's why that little oddity looks kind of out of place, if you will, in this table when you look at it and you see that index 0 represents item 1. Well, why wouldn't it represent item 0? Well, realistically, I could have put item 0 in there if I wanted to. The reason I did mix this up was because I want you to clearly understand that the index doesn't relate to a numbered value in the right-hand side. It's simply a way of gaining access to the value. If I wanted to pull item 3 out of there, I would have to use the array's index 2 to actually get to that value.
So, Jerry, this is a good time to ask this question, I think. When we talk about data structures, are we really talking about just a type of variable? How does this relate to the concepts that you introduced in the previous slide?
Yeah, so really good question, and that is true, Paul, that the data structures will be represented by a variable. So you have to name them. So when we create an array, and we'll see this in the demo shortly, we have to give it a name so that we know where it is. Because again, even though it's a collection of items, a collection of objects that we're storing, the computer will still store that information directly into the computer's memory. And in order for us to gain access to it, it needs to know where it is. Now, in the case of the array, we will actually store in the array name the pointer or a memory address to the beginning of the array. And then the computer knows how to gain access to the rest of it simply by adding whatever our computer memory addresses are in order to get to those individual indexes. But yeah, to answer your question, Paul, absolutely, we're storing these as a variable, a single name, but rather than representing a single piece of data, they're representing multiple pieces of data.
Right, so if you think about the relating to the concepts we talked about earlier, a variable could store my first name and just my first name. An array might be able to store all my contact information, so my first name, my last name, my address, and other things.
Yeah, great clarification point. So, cool. So this is, again, very high-level overview of an array. We'll focus a little bit more in the demo to kind of give you a visual of what it looks like in the programming code itself, and we'll see how we can access the values for it. The next item we want to take a look at is a stack. Now, stacks are kind of interesting because it's not something that you necessarily have to deal with on a regular basis in programming. You won't always be creating stacks in your code unless you're doing specific types of programming. And you might consider, if you're somebody who gets the opportunity to work on an operating system, that you will deal with stacks, because this is how we store program instruction pointers and data. And we'll talk about that in just a second. But you know, as we look at the visual that I've used here, again, a stack is a collection of objects, but we access it through a couple of different methods called pop and push. And the visual or the image that I've used on here is a stack of trays that you might find in a cafeteria. And if you look at this particular structure of trays, you are not able to access the tray at the bottom of that stack. There's no way for you to pull that tray out of the bottom of that stack without obviously damaging the structure that's holding it, and we don't want to do that. But it's important to note that in order for you to get to the bottom tray, or in order for you to get to tray number 20 or 26 or 35, you need to remove all the other trays off of the top of that first before you can gain access to it. So when we look at a stack, we can consider, when we put values on the stack, programmers say we push the value on the stack. And when we take a value off the stack, we pop it off the stack. So it's important to remember that, you know, when we put values on the stack, we're putting a value, and then the next value, and the next value, and the next value, and the next value, and our stack continues to grow, pushing the first values down. We can consider a stack to be a data structure that's known as a first in, last out data structure. So the first value that goes into the stack is typically the last item that comes off the stack. And I remember when I was working as an instructor teaching some programming classes, that I had a student ask me specifically about how do we know in our code, when we say we reach a decision structure or point where we branch off and go do something else in the code, how does the computer know where to come back to when it's finished executing that? So we've got code that's executing sequentially. We hit a point where we branch off and go do something else. We've got to come back to continue that execution. And so I use this analogy to explain to them how the operating systems and the compilers use the stacks to represent that. As the code is executing, we are pushing data and instructions onto that stack, and we continue to build that stack. And when we call this other function, when we go off and branch off, we now push that new instruction on top of it, and then all of the data that we need. And as the function executes, it starts popping its instructions and data off, and we keep bubbling back up until we get to the point where that last instruction was. So that's kind of the way stacks are used in a real-world scenario in computer programming, just to give you an idea. The next one we look at is a queue. And again, it's a collection of objects, but we access a queue through queuing or in-queuing a value and taking it off through a dequeuing. And I use this one to represent something that would be similar to a line at the motor vehicle branch. This is considered a first in, first out type of a data structure, where the first piece of data that's into the queue will be the first piece of data out of the queue. And you access that information through these different methods that pull the items off of the queue. Again, it's very kind of abstract right now when you're looking at it and thinking, well, how does that work? But as we view the samples, the way we've written the code samples, you'll actually see how the data values come off of the queue and off of the stack in the specific order that they work. So, if you have questions about that, just kind of hold them for a second. When you see the demo, you'll get a better understanding of how they work. The last data structure that we'll take a look at is the dictionary. And again, it's a collection of objects, and I'm using the term object loosely here because when we get into the object-oriented programming section of this MVA Jumpstart, object takes on a different meaning. But for our purposes in this one, think of an object as a character, a string, any kind of a value that we want to store. They're just collections of those values. So it looks similar to that array that we looked at a little bit earlier. The table looks kind of similar. We've got text values on the right-hand side. First item, second item. These could be number values, it could be single characters, whatever we want to store in this. But instead of accessing these values through the use of an index like we did with the array, instead we'll access these through the use of a key. And sometimes programmers prefer to use a dictionary type of a data structure because it's much easier to know what the data value is that you're pulling out through the use of a key as opposed to the use of an index. Going back to the example, that Paul's brought up a couple of times about filling out a form with his first name, last name, all of his contact information. we can store that information into a dictionary, and the key would be first name, and the data would be Paul, and then the key would be last name, and the data would be Party. So it gives you an idea of how that dictionary, it makes more sense from a logical perspective of how you would pull that information out of the dictionary item itself. All right, enough about me talking. Let's go ahead and take a look at a demo of some of this information and what it is that we will go through in figuring out, or I guess demonstrating, if you will, all of the different data structures that we have available. So I've got Visual Studio 2013 up and running here, and we're going to take a look at the different data structures that we just talked about using the values that we had in the tables that were displayed. So this instance, the first thing we want to take a look at is our array. Now again, from the perspective of looking at the code here on the screen, don't get yourself too wrapped up into what the individual keywords mean. I'll explain some of them, and we'll talk about how the functionality works a little bit on these values, but it's just important for you to just see how these data structures function from a coding perspective. So in the array sample, we've created an array, and here's an example of what Paul talked about where he said, are we using variables for these data structures? Yes, we are. And my array is an example of a variable. And this one, we've told it, will store string values. So that's the data type that we talked about. All right, so we've created a variable to store data types of strings. Again, don't worry about the syntax. These little brackets just simply mean this is an array. It's a C# syntax that we're using. And we create the new array, and now we're storing values. Item 1, item 2, item 3. These are string values that we stored. Again, same as what was represented in the previous slide that we talked about where we had the table for our items itself. Now what we're going to do is we're going to iterate through this array and do a couple of things. And the iteration actually comes down here in this little for loop. And we'll talk about what that's doing. But this, more importantly, is the access of the array from an index value perspective. That's what this line is going to do for us. This console write line, you'll see when we run the code, will simply display the values for us on the screen. But what we're going to do is, here's the index value of that array. So we're going to pull out the value that's stored at index 2. Right? So we'll show you again how we're accessing it using the index value itself. So let's go ahead and execute this real quick. It will build, and then it pops up into a console window on the screen. And you'll notice at the first line here it says item at index 2 is item 3. And if you're not sure, let's go ahead and take a quick look. Item 0, item 1, item 2. Remember, arrays are 0 based. So index 2 pulls out item 3.
And notice that you don't have to assign the index value. As you're adding items to the array, they're just added in the order according to when they were put into the array. So 0 will be the first item, 1 will be the second item, and those things. You don't have to actually assign those numbers.
Correct. Yeah, and it's that brings up another point too, where Paul talks about putting the items into an array. Arrays are typically accept the values in whatever way that you put them in. You can, when you create the array, we actually created it, item 1, item 2. So we created the values in a alphabetical order, but they might not necessarily always be in an alphabetical order. A little bit later on, as we start talking about algorithms, you'll see one where we have the ability to sort an array, which is something that we might want to do. Because the values put into an array, we might create one dynamically as the code is executing, and the values may not necessarily be in a specific order, and if we want to order that, there are different ways that we do for changing the order of the values in there. But again, as Paul said, we're not telling it I want to store item 1 at 0. We're just saying I want to create a new array. Here's the values I want to store in it, and the compiler handles dumping it into the array in the order that we've specified. So it is important to note that because the order was specified here, that's the way the values got put into the array, only because it was the order that we put it, okay? So great point, Paul. Now, so the last thing that we did was there was a little for loop. We iterated over all of the items, and just again, this is a way of showing you this is what the array contains. So it's a way of outputting it to the screen. And that little piece of code that we dealt with was actually in this little for loop here. So this was a repetition structure. We're going to focus on those in another module, so don't worry too much about what this does specifically, but it's just iterating over every value in that array and outputting it to the screen. So that's an array. That's basically how the arrays function. That's how you create an array, specifically in C#. and how you can access it through its index value and how you can iterate through and push the values out or display them on the screen itself. Now what we're going to do is take a look at an example of a stack. And in this case, we're going to create a stack. Again, here's our variable name called myStack, and we're going to put items into the stack. So if you'll notice, we're using the push method. This is simply a method of the stack object in C#. It's a way of putting the values into our stack. So we're going to push values in, 10 items altogether. They're string values. Then we are going to come down and we are going to display the count. So just to verify that we actually have 10 values in this stack. Once we're finished with that, we're going to kind of iterate through another looping structure. And what we're going to do is we're going to say, as long as the stack contains values, as long as the count of numbers in there is not 0, then we will pop an item off the stack. And it's important to pay attention when we pop an item off the stack as to how they come off. All right, and we'll output some text that says what we're doing and kind of shows you those values. But before I execute the code, notice the order in which I put the values onto the stack. I started with item 1 and I ended with item 10. Remember, the stack is a first in, last out, right? So what does that mean? Well, let's execute the code and see what happens. Let's go all the way up to the top. The initial count is 10. I popped an item off the stack, and here's the key differentiator on that stack. Item 10 came off the stack. If we go back and we look at how I pushed the items on, I pushed item 1 on first and item 10 on last. So that shows you how the stack functions. Item 1 did not come off first. Item 10 came off first because it was the last item we put on the stack. Go back and look at that image that we had of the cafeteria trays in that little container, and you can consider item 10 as being that top tray. So we've just popped that off, and we've lowered our count of the stack to 9 because there's only 9 values left in it. So that, again, it's important to note that as we retrieve the value from the stack, we're actually taking it off. The array, we didn't. We just looked at the value that was there and said, thank you very much. But here we're actually removing the item with the pop. So we continue to count all the way down until we finally removed item number 1, which is the first one we put on, is the last one to come off, and our stack count has now gone back to 0. So again, just an example of showing you how a stack actually functions within the programming environment. How you interact with it may be different depending on the programming language that you're using, but that's just a generic way that a stack functions. All right, now we'll have a look at our queues. Again, remember that a queue is kind of opposite to the stack in that a queue is a first in, first out scenario. So we're creating a new queue called myQueue, and we are going to put items into the queue through the use of the enqueue method. And we're, again, putting them in the same order that we did with the stack, item 1, item 2, item 3. The queue has an interesting feature in C# where we can take a peek at what that first item is. So that's what we're going to do. We're going to look at what that first item is. We'll take a count just so we can verify that we actually have 10 values in there. And then we're going to dequeue an item. Now you'll notice here I haven't said what item I'm dequeuing. I've just said dequeue. What we're going to do is output to you what that value was that we dequeued, and then we'll show you how the count has been decremented, and then we'll look at what the new first value will be in that queue. Let's go ahead and execute this. So again, the first instruction that we executed here was a peek, right? And that told us that the first item is item 1. Then we said, give me a count. How many items are in the queue? There's 10. Then I called dequeue. Again, I didn't tell it what I wanted to dequeue, but because it's a first in, first out, it dropped off item 1. So item 1 comes out. The queue count is now 9. I only have 9 items remaining. And I run that peek one more time, and it now tells me that item 2 is now the first item to come off of my queue. So if I were to run that dequeue item again in here, then item 2 would come off. It would show me item 2. My count would decrement again by 1. We'd be down to 8. All right, so a little bit of the opposite of how that stack functioned, where the last object was the first to come off. In this case, the first object was the first to come off. So that's your queue sample. Let's comment that out, and then take a look at our last data structure, which is the dictionary sample. And in the dictionary sample, what we're doing is we're creating a new dictionary. Again, here's that variable name, my dictionary. And it's going to store string values. That's simply all that these mean in here. And then we have our keys, and we have the values that are be represented by those keys. So we add 5 items, and then we will go ahead and randomly access a value in that dictionary by using the key. And then we'll show you how we can actually remove one. So let's go ahead and execute. And we can see that it simply says that the item represented by key 3 is known as third item, right? So again, it's not an index value, but it is by using the key, so it's a string value. You can see how it might allow you to gain a little more insight into what your code is doing, because now you have the ability to understand if I'm accessing a value, the key would be a much more visual representation, if you will, of what data you're going to pull back, as opposed to the array, where it only deals with a numeric value, right? All right, so that's our data structure demo. The next thing we want to take a look at is the concept of an algorithm. Algorithms can be mathematical formulas, or algorithms can be recipes. Algorithms can be a bunch of different things. You know, consider an algorithm as the solution to a problem. And that's kind of the way, software developers look at an algorithm. It becomes a solution to a problem. And realistically, that's what your product owners come to you with as a software developer. I have a problem, help me fix it, help me solve it. You will create an algorithm that is designed to solve that problem. So let's see a couple of examples. One is a real-world example, and one is kind of a coding example. So if we switch to our slides, we look at an example on the left-hand side. Might be an algorithm that you would focus on for cooking pancakes first thing in the morning for your breakfast. We start off at the opening where it says Start Pancakes, and we're going to add eggs, we're going to add flour, we're going to add water to the mix, then we'll mix it all up. And then we look at it and we say, is it the proper consistency? Yes or no? If it's not, we say, well, what's wrong with it? Is it too thick? Yes or no? Well, if it's too thick, then let's add some water. And then that thins it out, we mix it up again, and we check for the consistency again. And if we're fine, we'll go on and pour it in the pan, serve it and eat it, and we're done. But if we put too much water, well, then we got to go back and iterate through this again. So you can see how the flow is kind of taking place in this recipe algorithm, if you will, in that we go through the process of thinking logically about how we make the pancakes. Without thinking logically, you just get up in the morning, you crack the egg, you throw the flour in, you mix it up, and you go, yeah, it looks good enough, throw it in the pan, you cook it. But this is a logical way of looking at it. This is breaking it down into the discrete aspects. As Paul and I were going over this process, we kind of looked at this algorithm for pancakes and realized that there's a bit of a bug in here. And it's important to know that this is why we write things this way. This is why you visualize your algorithms in such a way. And what the subtle bug here was, if you look at the slide again, we see that we had a check to see if it was too thick. And we said if it was, we would add water, and then we would mix and we would check for proper consistency again. But what if we said, no, it wasn't too thick, right? So in other words, it's too thin. So we said no, and if you follow that no path back up, it says, well, let's add flour. But notice what happens next. We immediately add some water again, which that's a bug, okay? So if we did that without thinking about it in our morning routine, we would end up in this infinite loop where we would say it's not the proper consistency, it's definitely not too thick, it's too thin, so let's add flour and let's add water and let's just continuously repeat that. So this is why it's important to visualize your algorithms, and it helps you pick up these little subtle bugs and potential problems that come through. Now let's bring that over to a programming perspective. On the right-hand side, we have something called an algorithm for a bubble sort. Now, it's also important to note, you might have some of you out there viewing this that go, hey, I've programmed before, and Jerry, your bubble sort is not correct. It's not complete, okay? It's not correct, it's not complete. I didn't design it that way because there's a little more complexity in a bubble sorting routine. But it's just to give you an idea of how you might look at it from a programming perspective. You've already seen the arrays, so you know that we have an array of values, and we've stored them into that array collection. And what happens if they're out of order and we want to sort them? What a bubble sort does is it says I need to compare two values and determine if one is less than the other, and if they are, I need to swap them, right? So I want to put the lower value first and the higher value second. So that's what this bubble sort does, is it gets the first value, so we say get value 1, then we say get value 2, and then check, is 2 greater than 1? Well, if it is, we're going to swing off to the right and we'll swap 1 and 2. And then we come down and we check to see, are we at the end of the list or the end of the array? If we are, hey, we're done, sort of. And this is where this bubble sort routine is not complete, and I'll talk about that in just a second. But what about the other value, right? So we check to see if 2 is greater than 1. If it's not, well, let's check to see if we're at the end of the list. If we're not at the end of the list, then we need to increment the values. So in other words, we need to continue looping through these values in this array, continuously checking 2 values, one ahead of the other, one after the other, to see whether one is less than the other, and do this whole swapping routine. But where this is not complete is that a bubble sort routine is probably one of the slowest, most inefficient sorting routines that there are for trying to sort a list of values. And the reason why I say that is, consider that we have an array of 10 values, and we go through the process of iterating through it. What happens if we have numeric values 1 through 10, and number 1, the value 1, is at the very bottom of that array? How many times do we have to iterate over that array before we bubble 1 all the way up to the top? Well, we're going to have to go at least 10 times before we get to number 1, and then we have to swap number 1 for place 9, then swap it from place 9 to 8, then from 8 to... So you can see how this continues to be, we go over this loop numerous times until we get 1 all the way to the top, but then 2 might be the next one down, so we've got to go through that again. So we'll continuously iterate through this loop until we get these values all in a sorted order. So we're going through this loop multiple times, 10 values, computer will do it relatively quickly. Put 1,000,000 values in it and see how long it's going to take, right? So this is not an efficient sorting routine, right? But again, this is just to give you an idea. This is what an algorithm looks like. This is how you might visualize it before you actually go through the process of writing the code to create that. Now let's take a look at decision structures, our next section in this module. As you saw in those algorithms, we had these little triangular boxes or diamond-shaped boxes that ask questions. So your code will always be asking questions. You'll always be looking through your code to say, do I need to do this? Do I need to do that? Is this greater than this? Is this less than that? Is this equal to this? These are all decisions that you will do in your program itself. So the different data or decision structures that we have available for programming, and again, some of these can be programming language specific, but you'll focus on 2 pretty much common ones: an if decision structure and a switch or select case. Now, select case comes from our Visual Basic language. Switch comes from our C language. C, C++, C#, Java, they all use the switch, and they will use the if and the if-else if. These decision structures allow us to evaluate a condition, take a look at whether it's true or false, and then take an action based on that. And that's essentially what they do. They allow us to change the flow of our code, so we can implement branching in our code to go where we need to. In the days of the VIC-20, the days of basic, beginner's all-purpose symbolic instruction code programming language, we used things such as goto and go-sub, and everybody didn't like them because they created things called spaghetti code. It was very difficult to keep track of where you were at. So instead we make use of functions now, which are discrete pieces of functionality that our code uses, and we can change our program flow based on what the outcome of these decision structures are. So without too much conversation on that, let's go ahead and take a look at an example of some decision structures. If I can find I know I have it here somewhere. There we go, there's our decision demo. It's much easier to kind of understand how these decision structures flow if we look at them from the coding perspective. So here we're going to take a look at the if decision structure at first, and it comes in different forms, and we'll focus on each one. These variables that we've created up here just allow us to check these conditions as we go through the code flow itself. So our first sample is a quick and simple if one. We set up a condition variable and we assign it the value 1. And then in our if condition, we have the keyword if, and in the parentheses we have a condition or an evaluation, if you will, for lack of a better term. We need to evaluate what the value of condition is currently set to. And we do it through this syntax of condition 1 equals 1. And we're going to take a look at if it's equal to 1, what do we do? So the way an if structure works is that it will execute code, in our case, this line of code, if this evaluates to a true condition. If it doesn't, this code won't execute. But regardless, this line of code is going to execute. All right? So it makes sense to see it in action. Let's go ahead and execute that real quick. And we can see that we output comparison evaluated to true, and we said that this line executes after the if regardless of the condition. What does that mean? Well, we set condition to 1, and we checked here to see if it was equal to 1, and because it was, this line of code executed. Regardless, this line was going to execute anyway. And to show you how that works, let me go ahead and change this value to 2, execute the code again, and notice that that line in the middle didn't execute this time. The line in the curly braces didn't, but the last line did. So again, regardless of the condition, that was outside of the control of that decision structure, and it executed anyway. Now, if you're curious about why I'm using a single equal statement here and a double equal statement here, this all deals with, again, very syntax specific from the code itself. In C#, a single equal symbol is considered to be an assignment. We are assigning the value 2 to this variable, whereas a double equal sign represents a comparison operator. Is this equal to or not? All right. So a simple if statement. Let's go ahead and comment that out because we want to look at the next one, which is an if-else sample. This is something that you would use if you're trying to determine whether a condition is true or if it's false, and to take action based on whichever one it is, right? So in this case, we're going to set the condition 1 equal to 3, and we're going to, again, do the comparison to see if it's equal to 1, and if it is, we'll execute this statement. But now we've got an else clause in here that says, you know what, I want to do something if that evaluates to false, rather than just the standard, continue execution from that point forward. If we execute this, you'll know that it says comparison evaluated to false. And it did that, so in other words, it executed this else clause because 3 and 1 are not the same. If I change that to 1 and execute it, then only the first one executes. It says comparison evaluated to true. Right? So the if-else structure is a way of saying, if the condition is true, I want you to do this, but if it's not true, I want you to do this. Whereas the simple if that we demonstrated the first time said, if the condition is true, do this. And I'm done. I don't care what you do after that, but I'm worried about if this condition is true, I want you to do this. In this case, we're saying, if the condition is true, do A. If it's not true, do B.
Is there any way in that algorithm that you just wrote to cause neither line to execute, the way that that's written?
So that's an interesting question. If neither line was true, what would happen, right? And in this case, no, because the way that this specific if structure is written is it will only execute something based on either true or false, okay? And if it's true, this first one executes. If it's not, the else clause executes. And then everything beyond that will execute regardless. So kind of going in a sense from your question, if we go back to the first if statement where the line executed regardless of the if condition, anything that's beyond this will execute. So if we didn't have a true or a false value, we wouldn't really execute, right?
Right, but the way that algorithm is written, that one of those lines will execute.
One will execute, right? Because that's the way the if structure works. Is it's based on Boolean algebra, essentially. So there either has to be a true or a false.
That's right.
I don't want to get into discussing nulls because that's a more advanced topic, but there is something called a null, which is kind of the absence of something, and that would more fit into the answer to that question. But in this instance, one of these will execute, okay, because it's either true or false.
Right.
Now we get into a little more complex one, which is an if else clause. And what this one says is I might have one condition, or I might have a second condition, or I might have neither one of those conditions. So this might come back a little bit to what you were talking about in that first one where we say, all right, I've got two variables, condition 1 and condition 2, and I want to check to see if condition 1 is equal to 1, and if so, I'll execute this. But if it's not true, then let me check to see, maybe condition 2 is true. Then I'll execute this one. But if neither of them is true, then I'll execute this one, right? So, we might relate that to a real-world scenario where I walk into a car dealership and I want to buy a Corvette Stingray, but I don't have enough money for a Corvette Stingray. and I don't have else money for a Corvette Stingray. I'd love to have one, but unfortunately I can't buy one. So my first condition evaluates to false, so I won't buy the Corvette Stingray. But my next else if might be, but what if I have enough money for a Camaro? And I do, so I'll buy the Camaro, right? But it might be, no, I don't have enough money for the Stingray, I don't have enough money for the Camaro, so I'm going to buy the Aveo, right? So that's kind of to give you an example of how this will function. Let's go ahead and take a look at what it does in code. So condition 1, we've set to 1. Condition 2, we've set to 2. Before I execute it, very quickly think, which statement is going to execute? And time's up because we're running it. So condition 1 is true. And you'll notice that none of the other statements executed, right? So it's kind of what we refer to sometimes as a short-circuiting. If the first condition evaluates to true, I don't need to check anything else. So the code just, it said, I'm done. Condition 1 is true. I execute that line of statement. Forget about the rest of the if statement. I'm done, right? So the rest of these are not even evaluated anymore, realistically, okay? So let's go ahead and say, oh no, condition number 1 is not true. So I've changed it to 3. We execute it again. Now because condition 1 was not equal to 1, we didn't print out that statement, but then we said, okay, well if it's not true, let me look at the second one, see if it's true. And it was, so we printed out the second one. And let's make one more change and make this not true or false. And you'll notice that neither condition is true. So that's how the if else actually functions. Okay.
And you can string those on indefinitely, correct? You can have else if.
You can nest those until you are so tired of nesting that you just don't know where to go anymore. And unfortunately, that's not something you want to get into.
Correct.
And because these if structures can be nested so deeply, you can actually get lost in an if structure that you've got nested, or multiple else ifs, else if, else, and it just creates this long string of code that you don't want to get into. As a result, we actually have, Paul is great at segueing into the next topic, so we have this structure called switch. And what the switch does, it gives you a cleaner way of checking multiple conditions and executing code based on that. So we set up something called a switch condition variable in which we're going to check a value. And the switch has a very specific structure in that we do the conditional check at first. So we have the switch statement opening, and we have our condition that we look at here, and we're going to compare it to something. And what we compare it to, or that something, is what's written in these case statements. All right. So these are the values that we will compare the switch condition. So consider this a little bit similar to saying, you know, like here we say if condition 1 equals 1, this is exactly what this is doing. Case 1 says if condition 1 is equal to this value here, I want you to execute these lines of code. Okay? So we've got switch condition set to 3. Let's see what happens when we execute this. You should be able to figure out which one's going to print. So we print out value is 3. All right? And the reason that we did that was because, well, switch condition was set to 3, and case 3 was where it evaluated to true, and we stepped into it. Okay? Don't worry too much about, you know, the whole syntax of this. As you start learning the program and getting used to the switch statements, you'll understand how these values function, what these different pieces are. But just know that this break statement is kind of important here, because this is the way for you to say, if this statement is true, execute this line of code, and then break out of there. So get out of this loop or this decision structure. We're done. Don't execute anything beyond that. All right. There are other ways that you can check multiple conditions with switch statements, but again, that gets into more complexity. But the last one that I did want to bring up is this thing called default. This is optional. You can include it or not include it, and this is kind of, in a way, it goes back to what Paul alluded to a little bit earlier. Is there a way of writing it so that if none of those conditions are true, something happens? And that's exactly what this one is designed to do. So we've set up a switch condition variable, and we've assigned it 5. And you'll notice that we don't have a 5 in any of our case statements here. We only have a 1, 2, or 3. So if I execute this case statement, it says the value is 5. So in other words, it said, well, none of these matched. So this is my default. This is what I will do if it doesn't happen. Okay, make sense? Perfect. So that is our little discussion on decision structures. Now we have to focus on repetition. Repetition is where we get into programs generating something that repeats or loops. And repetition is something that you'll run into in programming a lot, because it's something that is usually required to complete functionality in your algorithm. And we showed you the bubble sort. That's an example of something that will be done on a repetitive basis. We need to do a comparison, and we need to swap if something matches a certain value, and then we need to go back and we need to repeat that again. And so repetition is very important in programming, and we have different repetitive structures in programming that allow us to create the different loops that we want to do, so the different functionality. Let's go ahead and take a look at what we'll cover here are things such as for loops, while loops, do while loops, and my all-time favorite, it's not really, because it drove me crazy when I was learning programming, recursion, which is something that you will potentially encounter. Some programmers say you don't have to deal with it, some say you do. It's a great way of working with stuff. But we'll take a look at recursion. So what we're going to focus on is the different type of loops that we have, why you would choose one over another, and basically how they function themselves. So again, we're not going to talk to this one, we're going to demo so you can see visually how these things function. So let me go ahead and find my looping structure, sample code, and I've got way too many projects open here. So that was my class demo, this is errors, and this is looping, which is the one that we want to focus on. So we're going to step into our first looping structure we said was a for loop. And a for loop basically is a structure that says I want to do something repeatedly until a condition evaluates defaults. Right? So as long as a condition is true, I want to continue in this loop. And the thing that's kind of interesting is the for keyword is basically a way of saying, for each value in this range of whatever I'm working with, I want you to do something, okay? As long as something remains true. And each one of our loops, as we take a look at going through these looping structures, it's important to note that we should create something known as a sentinel value. And a sentinel value is something that we focus on in the loop that allows us to terminate it. And I remember as I was, again, learning my programming many years ago, there was a quote that I remembered reading from one specific author in a book that I was going through, and he said, we can create infinite loops, and infinite loops are loops that never end. And in terms of the programming world, an infinite loop is funny when it happens to another programmer, but not to you. But having said that, there are purposes for infinite loops. And in other words, you want to put the computer into a situation where it's continuously looping until something happens. A great real-world example might be, consider a game controller input. If you're playing on your Xbox console and you're moving your character around through the screen, there's actually a routine in the program that kind of runs, it's what we refer to as a polling routine. And it's a loop that runs continuously looking for the input from those controllers, so from the control inputs. And based on what you're doing, then it goes through the process of moving your character around the screen based on those inputs. Or maybe you squeeze the trigger to shoot something if you're playing a first-person shooter, or if you're in a racing game and you pull on the trigger and it accelerates the car. That's an example of a loop that is running continuously, but I wouldn't necessarily call it infinite because it does have an ending point, which is when we shut down the application, right? So, numerous times new programmers will run into this. They'll forget to do something with their sentinel value in the loop, and the loop runs continuously, and all of a sudden they get an out-of-memory error on their program because we've just filled up the stack in the computer, and we've halted the computer because we've taken up too much. So let's go back to our code quickly, and we'll take a look at how the structure of the for loop itself. Now you'll notice we got the keyword for, but then we also have some bits and pieces inside the parentheses. We have a counter, and this is what's known as the initialization portion of the for structure. So we declare a variable type, a data type of integer. We create the variable name called for counter, and we assign it the value 0. Always a good idea to initialize your variables in your code, right? Most compilers today will complain when you don't do that. They'll come up and tell you, hey, your use of an uninitialized variable. In earlier compilers, they didn't give you that warning, and so the chances are the computer would assign a memory location to that variable, but there could have been data stored in that from a previously executed program, and the data that got pulled into your code was not what you intended. So that was bugs in the program code, and it caused programs to crash. right, so we initialize. Then what we do is we have a condition. Let's go ahead and check to see if the for counter, or our loop counter in this case, is less than 10. And if it evaluates to true, we're going to execute this statement in our code, and you'll see that momentarily. The last piece is what we call the increment portion. And this one is kind of interesting because in a for loop, we actually execute the initialization and the comparison, but we don't do anything with this section just yet. We execute, if we were still in true, by the way, we execute this portion of the looping structure, and then when it's finished, this increment portion takes place. This little plus plus at the end is the same as saying for counter equals for counter plus 1. We're adding 1. We're incrementing it by a single value. This controls our sentinel value. Once we increase it to the value 10, this will evaluate defaults and our loop will stop. Right? Enough talk. Let's see what that looks like. Right, for loop, so we printed out at the top, this is a for loop, and all we're doing is we're simply outputting the value of that loop counter, right? So it's at 0, it's at 1, it's at 2, it's at 3. Oh wait, we stopped at 9. But didn't we say 10 was in here? Again, it's very important to keep in mind how these comparison operators work, how the counter starts at 0 instead of counting at 1. But in this case, we're simply saying as long as this counter value is less than 10, execute this. But as soon as it reaches 10, we stop. So that's why we didn't output 10. We only saw 9 as the last value that was output. Right. So again, very quick and simple. That is a for loop sample. That's how we do the looping with that type of a structure. We also said that we had a while loop. Well, what the heck is a while loop? Well, this is what the code looks like. So again, these are just statements we're going to output on the screen itself. In this case, a while loop is a little bit simpler looking than the for loop itself. So we have the keyword while, and in parentheses we have our condition, where we say while the counter, in this case we've called the variable while counter, while it's less than 5, I want you to execute these statements in the curly braces. Now, if you're wondering where the while counter comes from, again, we've declared these variables up here, okay? So while it's less than 5 and it's starting off at 0, I want you to execute this. But notice also that, unlike the for loop, we don't have an increment portion here. We also don't have that initialization portion. So we have to create the variable outside of that, so it has to be created ahead of time. We do the conditional check, and because we want our loop to end, we'd better do something with that sentinel value. So inside the while loop, we have to do the increment portion as opposed to the for loop where it took care of it in the parentheses up here. Right? So this is relatively simple on the while loop. So as long as the counter is less than 5, let's go ahead and execute. And again, you'll notice we stop at 4 because once that condition evaluates to a false condition, that loop no longer executes. All right? So we've stopped it on the while loop. Now, here's one that is going to kind of mess with your mind just a wee little bit if you're not experienced do-while loop, and will mess with your mind even more in the recursion example, but this one will kind of start you on the path of wondering, what am I getting into? So a do-while sample is similar to a while loop, and it's similar to a for loop with one exception. The while loop will only execute, as will the for loop, if our variable evaluates to true. Now, the do loop is different because we don't do that check until the end of the loop itself. So what does that mean specifically? Let's just go ahead and execute this for a second, see what it does. Looks exactly the same as the while loop. We spit out 0, 1, 2, 3, 4, and we stop. So theoretically, there's no difference between that while loop and that do while loop. But in practice, there is a difference. And here's the reason why. Because we don't do the conditional check until the end of the loop, the do loop behaves a little bit differently. So we're checking, I'm sorry for scrolling back and forth, I'm not trying to drive you crazy with this, but our value here is checking for a value less than 5. What I'm going to do is I'm going to set my variable equal to 6, okay? So that means that theoretically, this shouldn't execute because my condition should evaluate defaults. Or does it? So the do counter is at 6. Why did that print out, right? Why did we get something printed out there instead of not doing it at all? And again, the reason being is because the condition is not tested until the end. So the do loop essentially says, do this, and then check this. And if it evaluates, we'll stop. Right? So that's the difference between the while loop and the do loop. And you have to be, or the do while, if you will. You have to be careful about your considerations for doing that. But why would you use a do loop versus a do while versus a while loop? Well, maybe you want to output something to the screen, or you want something to take place regardless of what that condition will be. So maybe we want to let somebody know we're in a routine, and we'll check something later. So we need to output a value, or we need to do something regardless of what that condition is, and then we check to see if that condition has changed. So there's a couple of different ways of looking at it from that perspective, right? All right, last sample that we'll take a look at here to end out this session is recursion. And again, as I said, we will really mess with your mind on this one. I know that if I don't program these often enough myself, and I come back and I take a look at them, I really have to go and spend some time thinking about what this recursive function is actually doing. Because it does. When you can overthink these very easily. You can overthink these, and all teachings that I've ever had on recursion says don't overthink it. Just focus on the core of what it is. Let the computer worry about the repetition aspect of it. Okay. So again, we're just going to output some values to the screen here, but then we set up a variable called value, and we're going to store a data type of long inside this value. But here's something that you haven't seen yet, and this is what's known as a function call. So we're going to actually call something, which is this function called factorial. And we're going to pass it in a value of 10, and we're going to basically let it do its thing. And then we're going to end up seeing what the value is that resulted from that function. So if you're familiar with mathematical concepts, you'll probably understand what factorial is. If you're not familiar with mathematical concepts, let me briefly explain what factorial is. A factorial is a way of saying I'm going to take a range of values, you tell me the upper limit, and I will tell you what all of those values are multiplied together. That's essentially what factorial works out to be. And so let's go ahead and look at the code, and we'll see what that specifically means as we execute this. And I'll execute it quickly. You'll see the value, and then I'll kind of do a little step through it. It might take a little bit of time here for you to step through it, but it really helps you understand it. Again, remember how we talked about computers are very good at doing this and very fast. So we've got our value back, 3,628,800. You're probably looking at it and thinking, what does that mean to me? How did you get that value? How does that make sense? We're going to talk about debugging a little bit later on, but this is kind of a neat function within most integrated development environments, and I love the way Visual Studio does this. It allows us to step through our code one line at a time to see what's taking place. So let's go ahead and run this code again. But this time you saw that our little console window dropped away real fast, because what it did was it came back and it stopped on the code, and it said, oh, you put a breakpoint here, so we'll execute the code until we get to this point. And then I'll stop, because what I want to do is show how this is actually going through the process of functioning. So this line of code executed up here, this long value equals factorial with 10, and it basically said, I want you to go out and call this value, and we're passing in this thing called n, and if I hover my mouse over, you see it's the value 10 that we passed in from that function call. And so I can step into this one line at a time, right? So you can see this step into. My code will start to execute one individual line at a time. Now, here's the important thing that I was always taught. The instructors when I was going through recursion were telling me, just focus on the simple thing, and the thing to focus on is this little piece. If the value passed in is equal to 0, we are done, and we return 1, and that's a way of saying we're finished. We're finished this recursive execution. This is the piece that gets complex. If you're trying to sit here and put this in your mind and hash it out, mentally inside your head, and yeah, I know there are folks out there that can do it, but you're probably a lot smarter than me if you can figure it out in your head. I try not to. I let the computer deal with it. But this is the complex part, because it's like looking in a mirror that's looking in a mirror, if you will. So you're going to do something repeatedly. But again, we have this whole sentinel value that kind of breaks us out of that. So let's step into it. We know that the value n is 10. Let's kind of execute this. Oh, so you see what happened is that we did a comparison. We said if n is equal to 0, we want to return. But because it evaluated defaults, we skipped this, right? And we come back here now and we say, I want to return. And this is just a keyword that says, I had somebody call this function. I have to send a value back to that caller, right? It would be the same as me saying, here's a $20 bill. I want you to run down to the store for me and bring back a jug of milk. That's kind of what a function and a return is all about. We're kind of doing that same thing here. In this case, we're going to return 10 jugs of milk, if you will. But we're doing something differently with it. So we say I want to return that value multiplied by, but not a specific value. Darn it, we're multiplying it by calling this function again. So in the way code functions, or the way that the compiler evaluates this is it says, I can multiply n by this, but I don't know what this is yet. So I have to go call that to get the value before I can multiply it to n. And by the way, while I do it, I'll decrement n by 1. So I'll subtract n by 1 because we have to end this thing. That's our sentinel value. We got to get back to 0. So we'll do that decrementing portion. So what happens is, let's go ahead and step through this again. So notice that it said return n times factorial, and because it did that, it called itself. That's recursion. It's calling itself. So it said, I want to multiply, or I want to call factorial, and I want to pass in n minus 1. Because n was 10, now n becomes 9. Right? So watch down here in this window, and you'll see that value change, right, as we start stepping through this. So it's not equal to 0. We step over that, and we recursively call ourselves again. Now n has decremented to 8, and then 7, and then 6, and then 5. Right? So we'll step through this till we get back to the point where now n is 0. So we say I want to return 1. We step outside of our function. Oh, wait a minute now. How come that didn't go back to here where we're going to assign the value back? Well, it doesn't do that because I'll take you back to our concept of a stack. Remember how we said we're pushing values onto a stack, we're popping values off the stack? This is what recursion is doing here. Recursion is taking, every time we call that recursive function, we're taking that previous value and we're pushing it onto the stack. And then we're saying, I can't get at that yet because I'm calling recursive and I'm pushing another value on top, and I'm pushing another value on top, and pushing another value. When we get to the point where this n is now equal to 0, now we're going to start popping those values off the stack. And while we're popping the values off the stack, that's where the mathematical process takes place. That's where we start doing the multiplication. So back to our code quickly, and we'll see that the value of n will start to change. It's now counting up, because we're popping these values off the stack, and we're actually executing that value of n minus 1, and we're doing this multiplication now. So this is where we're multiplying those values over and over again, right? So we're doing 5, and then 6, and 7, 8, 9, 10. Now we've finished, because we can now we've popped all the values off the stack. We can now pass it back to the calling function, and when we continue to execute that portion of code, we write out the value to our screen, in which case our console window, well, it normally pops up, but when we're in debug, it kind of messes it up a little bit. Sorry. Back to our, I lost track of which one I was in, web demo class, errors, there it is, sorry, looping demo. Okay, so if we were to continue that execution, then the window would pop up. Because we were running it in a different mode, the window disappeared really fast. But you saw in the earlier version, when we didn't have the code on there, we got 363,682,800. If you think I'm pulling your leg, if you think that's not quite exactly what would happen, let me go ahead and run the Windows calculator. And let me go ahead and put in the values 10. Now, I'll do this on the numeric keyboard so you won't see me clicking the different mouse on here. But if we go 10 times 9 times 8 times 7 times 6 times, oops, my mistake, I did 6 twice. 5 times 4 times 3 times 2 times 1, we get the same value. So that's a long way around doing a simple calculation like this, but that's what recursion does. That's that factorial method. And the recursive function basically said, I want to call myself however many times you tell me to. I push all those values in the stack because I need to multiply them later. And then when I'm done, I basically do the multiplication. And because it was on the stack, and I showed you the calculation doing the calculator of 10 times 9 times 8, because that's the way the computer does it. It's popping 10, then 9, then 8 off the stack. So that's essentially what the recursive value did. All right, so that is our demonstration on repetition. And I believe we have completed this module. So this is your, again, to take a look at what it is that we've focused on in here. We covered some core fundamental knowledge that you need to understand as a programmer. We looked at what the data types are that you'll use in the computer programming. We talked about how the computer stores and processes information. We demonstrated the decision structures and the looping structures that you'll run across in your code, and just to kind of give you a really good core grounding in some of the key concepts that you'll focus on in your computer programming career. So hopefully you enjoyed that. Hopefully you got something out of it. And be sure to come back for Module 3, where we'll start talking about object-oriented programming.